Jeddah Tower already stands roughly 107 floors above the hot Saudi Arabian desert. Its massive concrete core has successfully climbed past 430 meters. The ghosted architectural outline rising above the current construction site promises a final height extending well beyond 1 kilometer. But as this megastructure prepares to overtake Dubai and the towering Burj Khalifa, the most unforgiving engineering challenge is not happening up in the sky. We have to look deep underground. Foundation engineering analysis for this unprecedented project actually predicted downward physical movement. The best estimate models anticipated a foundation settlement of roughly 90 to 110 millimeters. That measurement sounds frightening when you are building the tallest structure in human history, but it is not necessarily the dangerous number. The true structural problem only begins if those massive foundation zones suddenly stop moving together. When we hear that a skyscraper might sink, we instinctively imagine a catastrophic failure happening in real time. We picture a building slowly disappearing into weak sand or leaning dangerously to one side. But an engineered tower of this extreme magnitude does not actually need perfectly motionless ground to survive. In the world of geotechnical engineering, settlement is an expected physical reality, not an automatic failure. Think of a heavily loaded industrial elevator cabin descending down a perfectly straight vertical shaft. It can move downward as a single solid physical unit while remaining perfectly aligned and structurally safe. The skyscraper is safely supported as long as every single structural corner drops by the exact same microscopic amount. The immense physical demands change completely when one section of the foundation moves differently from the rest of the structure. How much the towering structure moves into the earth is significantly less important than how evenly it moves into the earth. The most fascinating detail of this entire 1-kilometer project might not be the historic height record itself. It may be the incredibly tiny spatial difference that geotechnical engineers desperately need to control deep underneath the surface. To understand exactly why different foundational areas would ever move differently, we have to look closely at what is actually carrying the weight. The deep earth beneath the active construction site is not a single identical block of solid, impenetrable rock. The geological material supporting this immense dead weight changes drastically at different depths and across different physical locations. Extensive structural engineering reports detail varying subsurface zones containing coralline limestone, siltstone, dense gravel, conglomerate, and deep sandstone. Every single one of these geological layers possesses a completely different physical density and vertical bearing capacity. Porous coralline limestone responds to heavy vertical pressure entirely differently than compacted gravel or hard sandstone. When you compress these materials, they deform and yield at entirely different physical rates. The deep ground simply does not behave like a perfectly uniform structural steel plate. These varying natural material properties guarantee a completely different deformation response when millions of tons of concrete and steel continuously press down from above. The geotechnical engineers knew that applying an immense uniform load to a highly non-uniform ground would naturally cause uneven physical reactions. The massive foundation design had to mathematically account for this vast spatial variation across the entire building footprint. To handle that highly uneven earth, the structural design team responded with an enormous underground structural defense system. They constructed a massive subterranean forest of concrete and steel right under the desert floor. The foundational defense system relies on approximately 270 highly reinforced board piles. Some of those massive cylindrical concrete columns extend up to 105 meters deep into the solid earth. They are meticulously tied together by a gigantic geometric raft that reaches about 5 meters thick in key structural load areas. When you imagine a human silhouette standing next to a 105-meter deep pile, it seems absolutely impossible that anything supported by it could ever physically move. But simply drilling incredibly deep friction piles does not magically erase the immense downward gravitational forces of a record-breaking megastructure. The deep foundation acts as a highly complex and constantly interacting physical support system. The massive concrete raft the deep friction piles, the varying subsurface rock layers, and the soaring superstructure above all continuously push and react against one another. The carefully engineered foundation is not actually trying to make all physical ground movement completely impossible. It is specifically designed to make that expected downward movement predictable, strictly managed, and mathematically controllable. That vital engineering reality leads us directly to the smallest yet most important structural number in this entire story. Picture a standard millimeter ruler sitting on an engineering desk. The best estimate engineering model for Jeddah Tower carefully described a specific differential settlement from the center toward the outer edge of the massive concrete raft. That precisely calculated expected difference in downward movement was less than roughly 20 millimeters. That is a physical structural distance significantly smaller than the width of your own finger. This tiny measurement is not evidence that the unfinished concrete tower standing in the desert is currently leaning or failing. It is the carefully calculated engineering threshold that the immense foundation system was originally designed to safely accommodate without causing severe internal damage. Engineers knew that the center of a massive piled raft generally settles slightly more than the edges because the vertical load is heavily concentrated in the middle core. Now contrast that incredibly tiny physical measurement with the massive vertical structural spectacle standing directly above it. We are looking at an architectural object explicitly designed to rise more than 1,000 meters into the sky. Which specific physical reality would actually worry you more if you were designing the tallest building on Earth? The entire massive concrete building moving downward into the earth as one perfectly synchronized and leveled unit, or one specific foundational section moving 20 millimeters differently from another section right next to it. A soaring megatower does not need to physically disappear into the ground for a serious foundational problem to officially begin. The first truly dangerous physical change is almost always entirely invisible from the outside of the building. If the massive concrete foundation raft moves perfectly together, the towering skyscraper remains geometrically coherent from the ground floor to the spire. But if one specific structural region settles just a few millimeters more than the rest of the raft, the physical deformation fundamentally alters how the entire building supports itself. The millions of tons pressing down from the sky do not simply vanish when the ground slightly shifts beneath them. Those immense vertical forces are violently forced to redistribute through the rigid internal structural system. They automatically start finding entirely different physical load paths to transfer their incredible weight safely down to the ground. A tiny underground spatial difference immediately forces the giant concrete walls above to carry the heavy structural load entirely differently than originally planned. Local internal structural stresses can change dramatically inside very specific foundational zones of the primary concrete matrix. The first real engineering threat is not the skyscraper rapidly sinking into the sand, but the invisible forces inside it shifting dangerously beyond their designed structural capacity. This critical structural reality brings us directly to a crucial operational fact about the giant unfinished structure standing out in the desert right now. As of August 2026, current media reporting places the active Jeddah Tower site at approximately 107 floors. Its massive concrete core has successfully climbed more than 430 meters into the sky above the construction site. That is already an incredibly massive concrete structure, but it still does not completely represent the final finished 1-kilometer tower. The complex foundation system is currently only carrying a fraction of its intended ultimate operational weight. Every single time a new massive concrete floor is successfully poured, the overall physical loading condition changes permanently. The massive underground foundational structure is continually being asked a much bigger and heavier physical question. Every major construction stage represents another critical operational opportunity to see exactly how the foundational system reacts to the increased pressure. The real physical behavior of the constantly growing tower must continue to agree perfectly with the mathematical engineering prediction created years ago. The structure standing today is essentially a massive real-world physics experiment slowly approaching its maximum designed load limit. The final finished structural condition simply has not yet been reached. Construction progressively brings the real structural system closer to the extreme loading conditions for which it was originally designed. We know this specific internal load redistribution matters immensely because the project's structural engineers already modeled it extensively during the design phase. The very first early version of the engineering analysis actually produced something the design team absolutely did not want to see. When they ran an initial foundation flexibility analysis, the computer simulation showed extremely high stress concentrations rapidly developing in the tower shear walls. If you looked at a structural stress map, it would visually show these specific vertical concrete wall zones turning bright red as the foundation deformed slightly beneath them. What physically happened underneath the immense concrete raft directly changed the physical demands placed on the skyscraper above it. This was definitely not a physical structural failure of the real building standing in Saudi Arabia. It was a crucial analytical discovery made early during the design phase that directly forced the engineering team to immediately act. It mathematically proved that foundation flexibility was so incredibly important that they had to deeply integrate the structural and geotechnical models. They could not assume the giant concrete raft was perfectly rigid, because even a microscopic bend could crack the walls soaring hundreds of meters above. This early discovery essentially proved that assuming a perfectly rigid foundation would completely fail to capture the true structural behavior of a 1-kilometer megatower. But long before the towering concrete structure could ever reach its ultimate physical test, it simply froze completely in time. Active construction operations stopped entirely for years, leaving the unfinished concrete core entirely exposed to the fierce Saudi Arabian sun and harsh weather. Time slowly passed. Desert dust settled onto the steel rebar, and the incomplete skyscraper stood silent against the rapidly changing local skyline. But the unforgiving physical engineering reality, waiting silently beneath the sand, never went away. When the massive project tender process was finally restarted, the main developers did not just blindly resume pouring new heavy concrete on top of the old frame. Project reporting heavily indicates that Jeddah Economic Company proactively commissioned a comprehensive independent structural assessment of the existing tower before tendering the new completion work. They needed to verify the absolute physical integrity of what had already been built and how it had settled during the long pause. The unfinished structure had successfully survived its unprecedented multi-year pause above ground. But the most decisive and dangerous loading condition still definitively lies ahead, because hundreds of additional meters of incredibly heavy concrete and steel still absolutely need to be securely built. The extended construction delay added a completely unscripted real-world chapter to the story of the foundation. The immense concrete structure had spent years sitting mostly idle, slowly interacting with the geological layers below without any new weight being added. To successfully and safely push the towering megabuilding safely past 1 kilometer, the engineering models and the real physical tower have to constantly mathematically agree. The structural design process fundamentally had to become a massive, continuous computational iterative loop. The highly complex geotechnical soil model mathematically predicted exactly how the varying underground rock layers would physically deform and move. The rigid structural building model then mathematically responded to that specific underground movement. That dynamic physical response instantly changed the structural downward loads coming vertically down through the massive concrete shear walls. Those revised downward vertical loads were then fed directly back into the foundational geotechnical model, which immediately changed the predicted ground response all over again. The deep earth changes the building changes the load, and the new load changes the earth once more. The published engineering source material describes this complex computational structural iteration, continuing repeatedly across multiple sophisticated design cycles. The engineers aggressively ran the interacting models until the predicted settlement contours matched closely within roughly 5 millimeters of agreement. What truly fascinates me as an observer is that the soaring architectural skyscraper and its deep underground foundation could absolutely not be treated as two independent physical objects. Each massive component constantly changed the fundamental mathematical engineering answer of the other, in an endless feedback loop. This roughly 5 mm convergence criterion physically proves exactly how much precise control the engineering team needed to maintain over the interacting structural system. Now take a moment to imagine exactly what happens if one critical assumption in that massive engineering model unexpectedly stops being completely true. This specific sequence is a strictly hypothetical failure path, not a description of current physical conditions at the active Saudi construction site. But it clearly reveals exactly what the primary structural engineers were fighting so incredibly hard to permanently prevent. If the actual measured differential movement on site eventually departs meaningfully from the expected analytical pattern, the deep foundation stops supporting the massive superstructure evenly. When that uneven physical support happens, the immense vertical building loads immediately begin to redistribute across the massive concrete raft. Some highly rigid structural regions, internally hidden inside the tower, suddenly experience vastly different stress demands than they were originally designed and reinforced to carry. The sheer physical geometry of the towering skyscraper above must physically warp or bend to accommodate that changed foundational behavior below. If that geometric deviation became sufficiently large and uncontrolled, the highly sensitive building systems would face extreme mechanical pressure. The high-speed vertical elevator guide rails, the precise architectural exterior facades, and the critical internal building piping systems would all have to absorb those immense twisting forces. A serious foundational problem in a 1-kilometer-tall tower does absolutely not need to begin with a spectacular visual collapse. It can begin entirely silently when one small section of the finished building becomes slightly physically different from the exact building the engineers originally thought they had. The truly dangerous moment is not when the massive structural skyscraper physically disappears into the ground. It is exactly when different parts of the deep foundation critically stop agreeing on where down actually is. Because that specific hypothetical sequence sounds so utterly catastrophic, we have to look very closely at the verifiable current reality of the actual construction project. The publicly available evidence used to heavily track this monumental structure does not establish that Jeddah Tower is currently experiencing uncontrolled or abnormal foundational sinking. The precise millimeter settlement figures and the analytical stress concentrations we just discussed come directly from the project design and preliminary engineering analysis. They are purely predictive mathematical models, explicitly designed to test physical limits, not proof of a present failure occurring on site. The hypothetical escalation sequence is meant to clearly explain exactly why differential settlement matters so immensely to a record-breaking megastructure. It is completely not evidence that this disastrous geometric sequence is currently tearing the real concrete building apart. But the absolute absence of verifiable evidence of failure does not make foundation settlement irrelevant. It explains exactly why the dedicated engineering team spent so much time, immense computational power, and concentrated effort actively trying to predict it. They proactively built an enormous subterranean structural defense system because the ultimate physical consequence of unexpected unequal movement is too catastrophically high to ignore. The massive deep piles and thick raft are doing their exact intended job of keeping the building structurally secure as it climbs higher. That profound foundational engineering challenge reframes the famous architectural rivalry heavily publicized across the Arabian Peninsula. The intense visible race for the ultimate world height record is almost always framed as Saudi Arabia versus Dubai. The current global architectural record belongs to the magnificent Burj Khalifa, standing proudly at 828 meters. Jeddah Tower is explicitly planned and designed to finally break the elusive 1,000-meter mark. But to actually achieve that unprecedented monumental milestone, the new soaring skyscraper does not need ground that absolutely never moves. It needs the highly varying geological ground, the deep concrete friction piles, the massive foundational raft, and the soaring superstructure to all constantly interact perfectly together. They must securely continue behaving within the carefully engineered and strictly monitored physical parameters of the entire integrated system. That specific strict requirement makes the race with Burj Khalifa far more structurally interesting than the highly publicized height record itself. The spectacular and highly visible part of Jeddah Tower is prominently happening high above the hot desert ground. But the truly unforgiving and highly complex part of the monumental project is entirely hidden underneath it. If the structural movement remains within the established design limits, the tower will safely continue its historic climb toward the clouds. The rivalry is fundamentally a battle of structural control, testing how well human engineering can master the unpredictable geological earth below. So could the unfinished Jeddah Tower actually sink before it becomes taller than the towering Burj Khalifa? The extensive structural engineering analysis already expected the massive foundational system to physically settle downward into the earth. Expected downward physical movement alone absolutely does not mathematically mean the towering structure is actively failing. Is there actual, verifiable evidence that the massive concrete core standing in the desert today is currently undergoing a dangerous, uncontrolled structural collapse? Absolutely not, according to the credible project reporting and professional engineering sources actively tracking its ongoing construction progress. The true structural threat, permanently hidden in the sand, is a differential movement significantly outside what the massive foundation system can safely accommodate. Jeddah Tower does not actually have to defeat downward sinking before it finally defeats the Burj Khalifa. It has to completely defeat unequal sinking. The fierce visible race for the tallest building in the world may be prominently happening far up in the sky. But long before Jeddah Tower can securely beat Dubai up there, it has to keep winning a completely silent engineering battle, strictly measured in millimeters down here. This video is strictly for educational and analytical purposes, based heavily on publicly available engineering reports, verified project modeling data, and current media construction updates. Engineering models represent early theoretical design predictions and complex structural analysis, not necessarily the current verifiable physical conditions at the active construction site. This analytical content absolutely does not legally constitute professional geotechnical or structural engineering advice. Do you truly think Jeddah Tower will successfully control these immense underground forces and finally officially claim the ultimate world record? Let us know your unique perspective down in the comments below. If you passionately want to deeply understand the highly complex hidden engineering systems driving these massive modern megaprojects, make absolutely sure to subscribe to the channel.